All right, so we started recording. We're in a new location. Um, one thing's for sure, the screen is sluggisher to come down. It's powered, and wow, started too early. Confirm and continue. Cancel. Let's go to Blackboard. By the way, have you tried the YouTube? Is it of any use to students that also come to class? Works for me too. I can I can watch myself and say, well, I need to maybe go less on tangents, or maybe some students like that better. Discussing about airplanes that go install in subs that never make it back to surface. Um, okay, so yeah, it's linked here now, and we'll play this YouTube. We'll discuss the properties of materials. We hinted already, we use some of them, but we'll be more knowledgeable now. There's a lab, used to be a lab in material science, actually several labs, 3 that pertain to this class. You'll see them the soonest next semester. Okay, let me do one other thing. And for this, let's see. So I need to bring. I have a PDF of the book. I'm not sharing it. It's copy. Touch logo to start. Huh. And then it will be down in downloads. Okay, so there is the FE type quiz tomorrow, right at the beginning of class, and then the first test on Monday, first hour of class. And what I'm going to ask you, or an invitation, not ask. So if you, as you try the recommended problem, you saw the list on Blackboard, and if you have you want a problem solved, I can do it on camera at home, and I can post the YouTube. Okay, I have a means to put the cell phone on top of my desk at home, and I can solve it. And or if it's just a specific question about any of the problems in the list, I can respond and copy everybody to the response. Okay, but don't neglect. You need to get some routine in trying problems on your own. The feeling that you know the material does not confirm when you have a limited time to solve problems in a test situation. Okay, so I used to solve more problem per chapter in the past. So let's do a quick, maybe not finishing the short marathon are never short, and look at these 2 problems here, maybe with a modification. So the first one here, it says to calculate the stresses in this step column, and it has loads applied at various locations. So I'm going to take a screen, print screen, and let's say paint. Okay, paste, and it will be this one. Just because it's a good excuse to show some diagrams that we can do on top or in parallel with the load diagram, as we call it. So again, you have a stepped column, or could have been vertical. This load here, it might be clear how it's applied. So you have the step, and you can have a collar, and this 1232 kilonewtons force is applied through that collar. This other one, the tensile force, think of a hole there, and you have a through rod and you plug. I remember as a student, I said, come on, professor, you asked us to solve this problem. How does it connect to the real world? Sometimes textbook problems tend to be, artificially created to, that is, some real world application might be simpler, but not all of them. Some are way complicated and you cannot do analysis by hand. Anyway, so we're going to do a free body diagram of just the column. So imagine this remove. I could go on paint and delete the ground. So you start looking. So some forces are one way, the other one or two towards the support, one away. We can assume that there's a net compression of the support. That is, you have a bearing stress here. You don't pull, say it's a welding. So this is a reaction at the support. This is a fixed end. So in general, we should, or a general loading, you should show here a vertical component, and then you should show a moment. Okay, so R, we have horizontal and R vertical, but these two that I added are zero for clear reason. We don't have any load that's perpendicular to the axis of the beam to cause the moment in the vertical load, or say you have a concentrated moment somewhere. We'll see this kind of problems later on when discussing beam bending. So this is just subject to some axial load, but the load is changing as you move along the column. And stress is likewise, and for other reason that the cross section changes. Okay, so let's calculate RH. So RH, or rather some forces in the x direction or the horizontal direction, we have equilibrium for the free diagram body, or free body. So what do we have? We have RH, and positive will be assumed to the right. So positive. I have RH, the unknown, and then we have plus 4.45 kilonewtons, and then negative 12.32 kilonewtons, negative 9.65 equals 0. So we solve for RH, okay, and that's going to be essentially this negative and these two positive. So it will be 1232, and then plus 964, and then negative, oh man, so 12.32 plus 9.65 negative 4.45 equals, okay, 1752, and positive 1752 kilonewtons. Okay, and now we can tell the amount of loading along the beam as we move from point A to the other end, correct? So if I do a cut anywhere up to point B, I'm seeing that portion of the beam compressed, and the stress would be the same because cross section is the same. So I can draw a load diagram, although I could, load diagram, and that will be for compressive stresses, so load. And let's show compressive. It would be best to have it align with the part. For that reason, I would need to move this up and to the elsewhere. Okay. Let's not forget we have one compressive load. And since I'm in pain, let me take the support off to make it clear. All right, so this was the calculated force, RH, 1752 kilonewtons. Okay, so if I go up to point B, I see compression by that amount, so negative 1752, and this is kilonewtons. Okay, and then at point B, what happens? If I am passing point B, I need to do a free body diagram of the, well, best is if I take the right-hand side, I would say. So if you go and, let's see, and it could be anywhere. Nothing happens right after B and right before C. So I take it, copy, and paste. And let me move it here. And we can show this will be the axial load F going between B and C, excluding N. So what is FBC? Essentially, we'll repeat the analysis that was here. I go back to recording to see the original drawing in place. So we say FBC, where sum of forces in the horizontal direction equals 0, and we have FBC positive, assume positive, it may change, and then I have, so FBC negative now, so I have positive to the right, negative to the left, 12.32, and then negative 9.65 equals 0. So I can calculate FBC will be a positive value. So it means between B and C, I have tension. Am I saying the right thing? So I assume this to, no, it's compression, because the what's left of the piece, which is here, there will be A with a B here, and then a C, and then a C. Well, C, it's already there. So I have RH, and I have this other force that's compressing. So yeah, it's away from, but it's towards, it's pairs towards the piece. So we have compression. Compression remains, but it will be less. So FBC on this figure is going to be a positive value, 1232 plus 964. And that's 21.96. Okay, so with that, do I have it right, the right way? So compression less. All right, so yeah, this diminishes, this is increases because these two act. Okay, that's fine. So we have more compression here. The diagram drops up to point C, and this is going to be negative 21.96. Negative because it's compressive force. So the stress will be a compressive stress likewise. I had to show the, so again, I did a cut where? I did a cut like here to find reaction, and anywhere I do a cut, I see the same compressive force. If I do a cut anywhere between B and C, I see this force acting, upon the, like you see to the right, and its pair, this is also FBC. It compresses the piece. We're looking at the left-hand side of the beam as a rule. So our analysis will go most cases from left to right. So it's a positive in the calculation, but I know it's compressive, put a negative. And then as I go past point C, I'm seeing, I'll draw a free body diagram. I could do the same. So draw a free body diagram of just, anywhere between C, past C, and right before D, I'll see the same thing. So it'd be 9.65 kilonewtons, and force F will be CD, between C and D. And I can show the rest of the column, not necessarily a scale, being compressed. Okay, and it has, some forces acting, the 4.45, and then the other one, 12.32 kilonewtons. And this is the RH. Okay, so what is this? And I no need to restate sum of forces in positive to the right. So FCD is going to be 9.65, but this is a likewise a compressive force. So I'm showing it on the diagram according with some negative 9.65 kilonewtons, or kilonewtons is here. So, okay, so was it clear? So this is the low diagram. Pum, pum, pum. And then the jump because of this force essentially what I have this portion of the column being loaded by this one direction and by this other one in the other direction, and what's left of was of this one. Anyway, so now we can draw the stress diagram, and it's just a matter of dividing these forces with a corresponding diameter. So the stress diagram is just going to be take the load diagram and divide by here and here by the same amount, 25 squared times pi over 4. And I'm showing compressive stresses as negative. So I'm looking at 17.52 over 25. And by the way, we have kilonewtons, so I need to work with, let's go in shorter steps. So between stress, and we go between A and B, A to B, we have negative 17.52 times 10 to power 3 to go to newtons. And area should be millimeter to get megapascals, remember? So stress would be in megapascals. So it'll be pi times 25 squared over 4. And then between B and C, I have this load negative. It's 21.96 times 10 to power 3 to go from kilonewtons to newtons. Diameter remains the same, pi 25 squared over 4. And then lastly, between C and D, I have the compressive load 9.62, negative 9.62 times 10 to power 3 over pi, and the new diameter is 16 squared over 4 megapascals. Is it clear what I did? So the load analysis, which is statics, okay, was the a bit more involved one. Dividing by the area to generate the new diagram, then we can we can look at the numbers. So proportions may or change with this one. So it goes a little bit, actually a bit more, and we don't know exactly how much because of the division with a smaller area than over here. Okay, so they are not similar figures because the diameter changes on the last section. Was it clear? All right. I think there's one additional problem in chapter 1 of this nature. All right. And don't hesitate, and in as much as possible to exercise your intuition. I sent an email, you probably got it, was just a screenshot. As I was checking the YouTube, I realized I jumped into explaining and forgot to turn a minus into a plus. And if you, like moments later, I looked puzzled because I remember that the link, one link was in compression, and those below were in tension. And then I said it's confirmed by intuition. So if you have like it was that truss, if you have and loaded from above. So if you think of a beam that's loaded from above, the below part of the beam is in stretch, and the top part is in compression. So at least from that reason, you would say the horizontal sections of that trapezoidal frame should be in tension, but we got compression, and that didn't look. I solved the problem before, but I went over it. So that's why the core agenda that I sent you. Okay, let's look at the, and it's again a matter of how do we do it? Oh, it's all because of the projector. Little we can do about it. Okay, so let's look at the problem that was on the same screenshot, which I need to take again. This one, where we need to calculate, what problem is this? 150. So print screen, go back to paint, select all, paste, and then grab it and cut. Select, paste. And what will be a good place to put it? Okay, maybe here. All right. So what do we have? We have a pin support, we have a roller, negligible friction, and we have an external force applied at the roller pin. Do you have questions? Let me know if you have questions. It's part of my job description to take questions from students. All right, and this is a round, it says rectangular bar, and then we have a pin. So we need to calculate the shear stress upon the pin, and we need to calculate the stress in the rectangular bar. Your intuition does tell you what kind of, do we have compressive or tensile stress in the horizontal bar? How many of you think it's tensile? Tensile stress. And yet, yes, this is firstly, it's a two-force member. Is it in tension or compression? It's in tension. Think of a wishbone. So you want to declare or think of a wish. Of course, you'll break from here, but think you also run a rubber band. Anyway, so we need to find the load upon the pin at D, and we can run the analysis from the perspective of what the other link A, B, C. No issues, but nothing changes really. The only one thing that does is to recognize that this same force is acting on this other side due to symmetry. Does that make sense? So if you do a free body diagram of the entire assembly, you'd see, you'd see the same force. Well, I can use the force tool, and I can put a red here. So it's like right here. Come on. Well, it has to say this way. I move it a little bit up, and then since I removed the ground, I would also have to show, in general, we have. Why can't you move? It's too small. So contact with the ground at the roller induces a vertical force. A pin also have a second orthogonal reaction force, but these two are, both equal 0. Do you agree? Why they're 2, 0? The reaction forces at the pin that I freed from its clevis, and where the roller contacts the ground. Why they're 0?
The force is orthogonal.
I don't have any, it's clear. You don't need to say sum of force in a y direction equals 0 and just say this guy plus this guy equals 0. I don't know how to put it. So it's clearly because of symmetry, because of the particular type of loading, but otherwise you wouldn't include it. If for example, if I move this force above, like somewhere here, I'll start seeing forces acting here because of the tendency of the whole thing to pull this up and press the roller into the floor. Okay. Well, if you think you need to go through all the small steps, that's fine. It's just that, I'm thinking FE exam. So that's not on us. By the way, did you know that exam takers from a different university, their pass or fail performance is relayed back to us? So, and it looks good on us if we can report to the state of Texas and elsewhere, other bodies, that we have, the percentage of passes from student taking exam better than in other schools. Okay, so we can do a free body diagram of just the left side link. This is 0. and it's going to be, I need to stretch my arm a little bit, will be like so. So I have the horizontal force F, and I have, again, we anticipate tension here, so it'll be tension acting, the part that was removed and tension, and this is paired to it. This would be F BD, okay? And then we have a pin which removed from its amount has two components. Will be RC vertical and RC horizontal. Okay. This was 0. I have a pin now. I removed the roller. Have a pin. This force, never name it. Should show here, but it's 0. So it tells us that this other force is 0. Okay. Does it make sense? So again, we don't spend time with useless little analysis when the result or the effect is clear. So this was FBD. All right, so we have this given force. What was it on the F problem 50? That was, come on, 50. So it's in pounds, 2,800 pounds. 2,800. Okay, 2,800 pounds. So this is the known, this is the unknown force, and I don't care about it. I want to calculate this one. So I could some moment about point C, and we'll end up with the unknown force, and that will be it. Okay, so I some moment about point C, it's equilibrium. I'm assuming positive for moments to be counterclockwise. So what do I write? I have already these distances. So if I begin from the bottom, I have, so put my finger there to allow rotate or mimic a pin about which it's rotating the beam. So I have F times, or 2,800 times 15 plus 30, that's 45. And that's a positive, just because of my choice of positive for moment. So plus 2,800 times would be 15 plus 45. Okay. And then this unknown force I want to find is going to be generating a negative moment that is clockwise. So I have FBD. Oh man, I always do this, but sometimes it helps. It's like genetic mutation then turn out from Australopithecus into a Homo sapiens. Without the mutations, you will still be, away from here. So that was 30. Thank you. Together they're 45. And then what is the arm of relative to C? What is the arm of? So this is the 30 inches. So times 30 equals 0. This is the unknown. I can solve for it. Once I have it, I can calculate the stress in the bar. The stress in BD, tensile stress, will be, so FBD. And this is a, it says rectangular bar that is 2 inches by 0.65. So it would be 2 times 0.65 equals. And then it says, is this double shear or single shear? Need to read the text of the problem. So that will be tau pin. Actually, both pins, if they're identical diameters, you should be expected, then it's going to be the same FBD times the area of the pin. So it'll be pi times 0.75 squared over 4. If this is single shear. If it's double shear, the two sides of the pin are going to share the load. So, or read the text of the problem, or FBD divided by 2 over pi 0.75 squared over 4. Again, this is double. This is single shear. Check the text of the problem. It may say if it's single shear or double shear. You can think it two ways. So either they share the load or you double the area because it happens in two places. Sharing the load might be more intuitive to declare the case. I do have here a pin that was used in an assembly, but doesn't look like being in double shear. Anyway, you can see the wear. So what happened, like load being applied, removed, apply and remove, and as the clearance increases, you have, the wear progresses more because you have more slack to accelerate over. So this is one specimen. The second specimen that I have, actually I have two and take care of them because they're more valuable than the brand new ones. I have two Woodruff keys. Let me show them to the online viewers. Pin that was worn out. And the key, Woodruff key is called, that was sheared. I'll post photographs of it, or of them, maybe on Wikipedia. Okay, so sheared Woodruff keys. Woodruff got the Benjamin Franklin Prize in the late 1800s for his invention. I don't know that's his full name. The engineer Woodruff got a prize for that key, but that was long ago. Now you get prizes for much fancier things. Okay, so this was a question about this problem. Was it clear?
I have one question.
Okay.
And I'm sure it's just if you assume the wrong direction, then it's just negative.
Uh-huh.
But for FDB, if you just assume that it's going clockwise instead of counterclockwise, we just get negative.
Here?
Yeah.
If I change this?
No, I mean like for FDD, it's kind of in the middle of those 2 points, the two arrows. You said FDB was the right arrow going to the left.
Okay, so
clockwise.
We're talking about this equation here, right? All right, so I'm assuming for some moments about point C. And I have two forces that generate one. The F force generates a counterclockwise moment, and I assume that to be positive. That was my choice. You can go the other way. It's like flipping the equation. And then this other force, the unknown, generates a moment that goes counterclockwise, and that's why I show negative. And then the arm of the force, now we work with arm of the forces because they're given. We can resolve them into a longitudinal perpendicular to the beam components. That's the alternative, and use these distances. Yeah. But the convenient way is to work it this way. And I think this is it. I don't know what
But if I assume that it was compressive instead
of okay, so you're
it would be just negative sign.
Yeah, well, correct, yes. So that will make this positive. You solve the equation, you have a negative here. Let's see. So I solve for this one, I get a negative value. No, I'm sorry. Yes, okay. So you assume, I understand your question. So you're just assuming this and this, but not knowing. Yeah, it's human. You don't have an intuition, goes all the way to the end. So that will change this into a positive. You get a force that is negative. It means that you have to go to the free body diagram and you need to flip it. You understand what I'm saying? So you need to flip it because the sign ended up being negative, and now it tells you that it's tensile. Okay? And only then you proceed to calculate the stress. Because the sign of FBD being negative, if you carry it here, it does and gets your negative sign, negative stress, which is compressive, does not show the. So you need to make the correction before calculating the stress. Okay, so there are two worlds: the free body diagram and load world, and make sure it's the correct one before you proceed to calculate stresses. All right, so we're going to return or go to the move to chapter 2. We anticipated quite a bit with here and there discussion. So in design work, and it's what you aspire to do, is maybe I should lower the screen. Or I'm lowering the screen. So you need to make decisions. Okay, design engineering is not textbook problem. You have the answer at the back end. You declare victory. So you have to make multiple decisions in terms of the material selection, and you have very many options. Sometimes it's hard to start somewhere or with something, but it all depends. So are you going to do one prototype and that's it, like they work on Kiwit? We have graduates that work on Kiwit and they build structures that, the next one may be different. Of course, they may use sub-assemblies anyway, or it's going to be produced in 1,000 copies, or we're going to be produced 1,000,000 copies. So if it's produced in large number, any penny counts. If you have 1,000,000 copies and you save 10 pennies, that will be a lot of money. Not that you'll see that money, but you'll be well seen at your job. Okay, so you need to look at various criteria. And so far, we have strength. We looked at it already. We discussed deflection. That has to do with stiffness. Okay, if you go to the machine shop, you haven't taken manufacturing, but you can introduce yourself to Jack Esparza and ask him to show you a boring bar. Not a makeshift boring bar, one that you buy. And you'll see it's heavy to hold, dense, and it's actually not made of steel, rather it's made of carbide. Why is that? Because carbide it's stiffer material than steel. And aluminum is less stiff than steel. And titanium is stiffer than aluminum, but not as stiff as steel, stuff like that. And then, when it comes to formability, ductility, as well as, ability to take variable loading, impact loading, all right? So glass or diamond is is known as, pure diamond is the hardest material known. But is brittle. Not that you can. Let's think glass. It's also high on the Mohs scale, and you can pop a glass baguette between your finger versus a nail of same size, which you bend, and it's much better to still have something in place, even if it yielded. Okay, and then density or weight, fracture toughness. I don't know if you know the story. It was Titanic. Back then they didn't have good control upon materials, and it was cold, like near or 4 degrees Celsius, the ocean, and the plates and the rivets, they behave brittle and they popped. Would have been much better for the rivets to yield and limit the gap. Maybe would have stayed afloat longer hours until rescue arrived. Machinability. Sometimes the sacrifice, you'll learn this in manufacturing processes, maybe you've been told in material science. So you sacrifice properties like strength or ductility to make it more machinable. For example, if you machine it on an automatic milling machine, on an automatic lathe, and if the chips are continuous and long, that's a problem, because you need an operator to pull them off, or they get entangled and break the spindle and stuff like that. So you like short chips that break by themselves, can be washed away. Okay, workability is a general that includes ductility, machinability, and then can it be welded? Low carbon steel, it welds better. Medium carbon steel still can do welding. High carbon steel, very difficult to weld, although not impossible. Like if you go to a welder and say, weld me 2 files together, we'll look at you. Are you serious? It's possible, but not that we do it and then appearance. If it's something that is visible to the consumer, like the housing, you made it, or what the, oh man, I could talk for the whole, you can tell I taught manufacturing processes. So like sheet metal, you can see the rolls imprinted on the surface of the piece, and it gets formed. You see other features, and you may need multiple coatings to hide those, not to be apparent through the paint, and that increase the cost just for appearance reasons. Some materials look better than others. You can also think of compatibility with the environment. So if it corrodes, aluminum can be as is finish, or you can do chemical treatment. And then stability. What is stability? It's dimensional stability. We discussed heat treatment, that quenching causes volume change because of the phase change. Material science, you had it. But that can continue phase change over time. So, for example, in rolling element bearings, where the clearances are so small, only certain type of materials are useful, because if there's minute volume change, you seize the bearing in a month or two after manufacturing. Cost, and availability. If there are strategic materials, the government has stockpiles of certain, they don't even know. It was a report years ago where it said and they listed some of the alloying elements. If the supply of manganese and chromium and two more materials stops for 6 months because of whatever conflict, the whole industry will be in trouble. Okay, so, and then compatibility with the environment and with the other materials in the component. Not just, so you design for what? For maritime use, pieces to be used on a boat or on a yacht is one. For example, I know of a case with a ceiling that collapsed. They used stainless. It was a cover for a swimming pool, but they add chlorine to the swimming pool, and that chlorine corrodes the stainless, and the roof collapsed after some time. Anyways, but we'll be looking at tensile stress and ductility, and this shows the stress strain curve for a ductile material like this stainless steel is. I'm showing it first to the camera. So this is a specimen, aluminum specimen, and this is only part of, I don't have the other piece of a stainless steel, okay? And just look at the way they broke. It's called cone in a cup, with a necking, a reduction in diameter. And we're going to look at the YouTube. Luckily, we can move left and right and observe what's happening. So on Blackboard, I linked apply strength. No, I'm where am I? Okay, YouTube, and no thanks. Okay, so this is a tensile machine, and this is how the specimen looks like. It's standardized. Length is 5 inches, and diameter is 1/2 inch, with good finish, not apparent roughness. They also do specimens for sheet metal. Okay, so this is an aluminum piece. Yes, it's an aluminum sheet metal, and originally was 5 inches. It got stretched before it popped, and just observe the way the fracture happened. It happened at 45 degrees. Then I have a cast iron specimen. I'm missing the other part, and look at the difference in the way the fracture is. So there's no necking. There's some cracks. You can see one of them about 1/4 of an inch away from the actual fracture, and then the rough appearance because of the graphite content. Okay, but yeah, let's have a look at this YouTube. It's 3 minutes, but I'm not going to watch. I'm just going to slide to the right. So look at the specimen. What happens as the force is increasing? This looks better in Google Chrome. Let's go to Google Chrome. No thanks. All right, so does it? Well, I thought it does. But a little bit fuzzy in the background, so just observe there's little diameter change, and then it maintains, the specimen maintains this cylindrical shape as the load is increased. And come on. This guy wants to be part of history. Can you see it stretching? It starts stretching, right? Can you see? Stretching, stretching. Now it's visible. So it stretches, and the neck starts developing. So it started. It was a slight reduction in diameter, but happened throughout, and then you start to have this neck developing, and then you have the neck that builds up, and I think we can watch it. Probably not the first time he's doing it, but hey, stammered. Okay, so look at the other one fell. This is the way the specimen, like in the fracture looked, like in the specimens, the aluminum and the stainless steel specimen that I passed around. Okay, so tensile machines. This will be a lab that you're going to do. Historically was done, or in the past was done for material science, but now you're going to do it in solid mechanics lab. Anybody registered for solid mechanics lab? You have a question? Oh, you missed the what? The fracture? Okay. Going in reverse. Yes, and then it stretches, and then you can see the about even, or it's even shrinkage, and then there's a neck that develops usually in the middle, but it's not as a rule. It might be some imperfection in the material that makes the neck in the fracture developing elsewhere than in the middle. This is for ductile materials like low carbon, medium carbon steel, and we'll discuss ductility in just a little bit. So again, the specimen is standardized. We have an area which you saw it changes, but the convenient way is just to assume or divide the load applied, which can be recorded with load cells, and divide that force by the cross section, the initial area. You don't update the area as it diminishes. This is an exaggeration of the strain. That is, change of length, which is also recorded by the instrument, divided by the original length. Original length, I said, is 5 inches. As you stretch it, that length increases. You subtract initial length, you get the length change. By the way, you can run this experiment in compression, but the specimen has to be shorter so that you don't buckle. And compression for brittle material is usually done concrete included. Okay, so what do? You record the load and you divide it by area. Initially, it gets you the stress, sometimes called engineering stress, and then the strain. That is, and it's unitless. It's the initial length minus, or the current length minus initial length divided by initial length. That's the strain. And this is a very steep, very close to vertical. So it's artificially moved away from the vertical line, and it's a straight line. Okay, and then you have, where it says A proportional limit, this is really the straight line. And then you have a point B, it's here, which is called the elastic limit. So it starts behaving non-linearly, but if you take the loads off, it comes back to the exact same length. That's why it's called elastic limit. Okay? So you stretch, it comes back to the exact same length. And then past this point, some material have this flat, or little change of stress, but a lot of strain increase. Not all materials behave this way. Not all ductile materials do, but some have this visible shape. And you continue applying the load, and you keep on dividing by the same initial area, and you calculate the stress, which again, some call it engineering stress. In manufacturing process, we call it engineering stress. And then there's a true stress, okay? And then there will be a maximum load that you can hold, the specimen can hold. And then there is a nose down because we have that substantial reduction of diameter, but you keep on dividing the load with the initial area, although the area is going down. In actuality, the stress keeps on, the true stress, if you update the area, you keep on taking measurements of the diameter and you update the area, the curve will keeps on moving up. Anyway, so this would be like the maximum. If you have a cable that you're testing, you rate the cable you're using in like elevators, for example, and you rate it for that load. Okay, it may be rated for that load, how much an load can sustain. And then you have the fracture. So due to the necking, it starts going down, and then you have the fracture. And this will be the maximum strain. And you can use the maximum strain, essentially take the full length, like the two specimens that I have here, both ends, and I put them end to end, like they, right before they separate, and I measure the final length, and then subtract the initial length, and calculate the strain as percentage. And if this is more than 5%, the material, it's accepted as being ductile. Anything below, it's assumed brittle behavior. For any plastic forming, you'd like the ductility to be as high as possible. Look at the specimen. This was some plastic material, probably polyethylene. Look at how much it stretched before it not even probably reached the travel of the equipment, of the tensile specimen. So this is called superplastic material. And also look at well, it's not material science, but look at the appearance. So this looks stiffer and more dense than the original material was. Okay. Likewise with steel material. So if for example, you're stretching the specimen and you pass the elastic limit and you stop after the yield point, and you let the load go, the specimen will, come back to a length which is more than the original length, and this will be the remnant deformation. And if you reload it, I don't think the book does not mention this. If you reload it, you will move, you shift to zero, to the new zero, and it will behave elastically longer because of what is called strain hardening. So you induce what is called strain hardening. This is how we get improved strength, cold drawn wire and thin bars. This is how, for example, if you take a pin and you heat it with a lighter at home, just make sure you don't burn your fingers. Then you can bend it easily. You heat it with a lighter, with a candle lighter, red hot, and let it cool. And you can see you can very easily bend it where you reheated. What you did, you've undone the strain hardening. This is manufacturing process that is. Maybe discuss strain hardening in material science. Have you? A little bit. Okay, so strain hardening. This is how you can improve strength and hardness to otherwise soft materials through cold working. You squish the grains, and this is how one way of doing it is through strain. The other one is if you roll it, if you compress it. Okay, strain hardening. That's why the condition is important. At the table, the back of the book, you look at the condition. If it's cold drawn or cold rolled, you'd expect higher tensile properties and likewise hardness than in a hot rolled state. Okay, so this would be for ductile material. We discussed stress and strain. The where the proportional limit is where there's a linear relationship between the stress and strain. So this would be essentially, although it was very minute deformation, this is where the specimen behaves like an elastic spring, but very stiff spring. It was a spring that, like rubber band. Yeah, well, that's not linear, but if it was a coil spring, you can see, they are really hard to stretch, but at least by hand. Anyway, so this is where we can assume the specimen, a tensile specimen, to behave like a spring. In compression, likewise, there's problems of combined materials that have different coefficient of thermal expansion, and how one and the other work together is like having springs of different rates being put in an assembly. For materials that don't exhibit that distinct yield line or yield region, we still assume a yield strength by or finding the point on the stress strain curve where, if the load is removed, the remnant deformation of the specimen is 0.2%, or strain is 0.002. Does that make sense? So you go to percent by multiplying this with 100%. And again, if I'm to run the the specimen loaded up to this point, take the load off, come back to here, treat it as a new specimen, 0 will be here, it will behave elastically longer. Does it make sense? And that's the strain hardening. So it behaves elastically longer. Okay, so if you run the test in compression, you would see the same behavior for materials that behave isotropic. For iron, for concrete, for concrete, the tensile strength is assumed negligible, never taken into account. You use rib bars to add tensile strength to slabs, like floor slabs, and then beams made of concrete. Cast iron behaves in compression much better than in tension, and you can account for that in the shape design. If you have ever looked at C-clams that were cast, they have a T section or an uneven I-beam section. Okay, we discussed percent elongation. Or let's discuss it just a little bit regarding the proportional limit on the graph. On this one, it's not shown, but on the earlier, so it says proportional limit, where this is a straight line. The equation, the stress strain equation that you write this way, has so this will be the slope of that line. It's noted E, and it's the modulus of elasticity, or Young's modulus of the material. Have you heard of modulus of elasticity? Okay, great. So this is sigma, the stress, load applied to the specimen divided by initial area. You don't update that area again. Sometimes, to be correct, you call it engineering stress, and then strain. Final length, or current length, minus initial length divided by initial length. It's unitless strain. Modulus of elasticity is a measure of the stiffness of the material. So, for example, if I have, 2 rods, you can easily show the difference. Same size, same length, same load, cantilever at the end. The one that's stiffer will deflect less than the one that was a lower modulus of elasticity. And the stress strain curves for different materials are shown here. Being stiffer, it's a more steep, that is, the slope of the stress strain curve over the proportional limit is higher for steel, less for titanium. Aluminum is even less, and magnesium is, of the 4, is the least stiff. So modulus of elasticity for magnesium is substantially less than that for steel. Titanium compares decently well with, and it's used, titanium is lightweight, pretty lightweight. I have a titanium rod in my office, and it's surprisingly light. Okay, so gauge length, and then percent elongation. So I said you put them end to end, final length minus gauge length over gauge length. And if this is more than 5%, it's assumed ductile behavior. And if it's less, it's assumed a brittle material. You saw in the YouTube as you stretch the specimen as it shrinks, right? So you can also record, now that it's commonly done, you can record the lateral strain. So it could be done on a round specimen, could be done on a rectangular specimen. So you measure initial dimensions, diameter or width, and then you record that over time, and that you calculate a lateral strain. This, due to volume conservation, but there's more to it. This will go, the lateral strain goes down as the axial strain is increased. You know, the reduction in diameter throughout of the specimen. That's before the necking develops. Okay, now we have what is called Poisson ratio. Have you heard of Poisson ratio in material science? Okay, so maybe I should move faster with this. We make the lateral strain, which is from this calculation ends up being negative, and make it positive. Take the ratio of the lateral strain over axial strain, and this is Poisson ratio. It's about 0.3 to most steel materials. Young's modulus is also varies little between various steel grades. So if you're looking for stiffness, that is, deflection is an issue. No need to go with higher grades just because of that. Anyway, so we have Poisson ratio as another property of the material. And then we have shear type of loading. I was telling you, shear tests are not as convenient to do with tensile tests. All you need is a specimen machine to size. Shear tests are done on tubular specimens with a necking, and you record, or you apply a torque that you measure, and you record rotation instead. And it behaves the same. You have a proportional limit, and you have yield if it's ductile material, and you keep on twisting until you break them into two pieces. And the rate, the proportional coefficient for that kind of stress or test in twisting is the shear modulus elasticity, or modulus elasticity in shear, noted G. You can see there shearing stress over shearing strain. And shearing strain is radians, which are assumed unitless. So both have units of megapascals of PSI or KSI, E and G that is, and they are related via the Poisson ratio. So if you have modulus elasticity in tension, which is the most commonly available one, and you know, yeah, it's steel and it should be around 0.3, you can get an approximation. I mean, you know, you can order if it's, you know, a critical component, more accurate calculations of maybe this one, because it comes from a tensile stress, and you can use the Poisson ratio. We'll use it when calculating torsional deformation later on. There are flexure tests done to assess the properties of material. That's done to plastics and elastomers in wood or concrete beams. You know, you support it and you apply a load in the middle, and you record deformation function of load applied. And then there's another property, likewise important, or important for design work and in applications. So hardness is resistance to wear. Okay, and hardness and strength, they go hand in hand. You know, you'd expect a hard material to be also strong, although hardness can also translate into brittleness. So, and for that reason, you may see parts that have heat treated done just on it. It's called case hardening. They're hard on a surface, but the core is more is softer and ductile to provide wear resistance on the surface and toughness. We'll discuss toughness just a little bit. The hardness test is the non-destructive one, and probably the easiest that you can do. All you need to have is just two parallel surfaces and the respective equipment. We have a harness, Vickers harness equipment in 118, where the tensile equipment is. I have here a specimen was a Capstone company in town, modified crankshaft for us, and you can see the places where they did hardness test. You can see it. You can even see if you take apart maybe a transmission, because they do random or process control, and they take a gear and put it on a hardness tester, look at the numbers, and may reject the whole batch. Or so you may see them, oh, that's perfectly fine. It just has just a little dent, and it ends up on the in use. Of course, not the same you can say with tensile testing. I mentioned last time Steel Dynamics here in Sinton, and they have a lab where they cut specimens, standard size for sheet metal, and they test them, and they affix a bulletin to the batch if there's a requirement from the, usually it is, we want this type of rolled sheet metal with these properties, and they run the test longitudinal, transverse at 45 degrees, the direction of rolling, because rolled sheet metal is not fully isotropic. I think you looked at this one, right? Okay. So regarding hardness, first was done was the way you do it, use an indenter. You press it against a flat finished surface. It should be a smooth surface, so you need to polish it to where you can measure the indentation. The Brinell hardness test, you force a steel ball against that prepared surface, and you measure with a magnifying glass the diameter of the indentation. The ball itself is standardized. The ball can be made of carbides, which is stronger than steel, and again was easy to do. All you had to do is just the load is standard, 3,000 kilogram force or 500 kilogram force. You just have a big weight, and you lift it and you let it over the surface. You take the specimen out, you measure the diameter. But nowadays, the equipment, they have a means to measure the amount of indentation. So these are the newer tests where the indenter is a diamond prism, and this is the Vickers test, and you measure the depth of the penetration. But the over 100, I don't even, we can verify like when the Brinell test was first introduced. That was more 100 years ago. I can tell you next or tomorrow after some research. Okay, so there are various test procedures and hardness scales. So you can see here Rockwell hardness. Harness RB. So there are B and C. It depends on the amount of force applied. If it's a soft material, you put too much force. So you need to anticipate the hardness to choose the right procedure and the scale for it. And then we have the Brinell test. And then so hardness C, you read it to the left. Rockwell B. So Rockwell C, hardness Rockwell C. Hardness Rockwell B, and then Brinell the Brinell is below. So you relate. Okay, so how do we go, for example, using this diagram? Let's take a screenshot of it to print screen. I go to Paint, select all, paste. Well, I can lower it for one thing, and I could draw lines in Paint. So if I want to convert from Brinell test to Rockwell B test. So I measure Brinell 200 number and then read the corresponding Rockwell test. See, it's a non-linear relationship between the tests. If I have a Rockwell C test, 200 moves, so it will be what, 15 points of Rockwell hardness C, which is all equal to like 93 Rockwell B. Does it make sense? You don't follow. You order pizza for tonight, folks? Play games? Oh, you want a 5-minute break? You want a 5-minute break? You can take it. You can take the 5-minute break. what? You're right. I need to pause the recording. But yeah, you can take a 5-minute break. So I'm going to pause. But I ask you first day of class if you want to skip the 5 minutes. Okay, so back to the discussion. I explained how you can convert between Brinell and Rockwell B and C scales, and then this shows how you can use. Well, it could be any of them, but how you can go between a hardness test and an estimate of the ultimate strength of a material. So I said that hardness tests are the most convenient. All you need to do is just 2 parallel surfaces with good finish on the one that you're pressing the indenter against. Machinists do another. They have, maybe you've been told material science. You take the you don't know what stuff is there. You check with a file. Can you file it? If you can, it's soft, and you can. If not, and you start guessing. But one way of doing it is just hold it against a grinder wheel, and you look at the sparks. So if it's soft, it will be big reddish color sparks. If it's whitish and small sparks, it's a hard material. But that's just qualitative, and it's done in industry. Anyway, so you see this equation. Oh, I need to go to the PDF. So an approximation of the tensile strength in KSI is half of the Brinell hardness number. So if you have the, maybe I'll just make up a problem. I'm giving you the Brinell hardness or Rockwell B hardness, and I'm asking you what's the approximate tensile strength, okay? And what would you do? Well, you need to move to this curve. So say I have 80 Brinell hardness B, you need to go to, well, 80 is too little, let's say 90, maybe 100, okay. I go to Brinell, okay, go to Brinell, and then from Brinell, go to this in this way. Or maybe all the way straight to this curve and read it this way, say. This is not quite diagonal like 45, but a regression curve through it would be, would justify this equation. Slope 0.5, that is 45 degrees. Anyway, so this is to get an idea, like the numbers, the hardness numbers you'd expect based on the conditions. So low carbon steel annealed, tensile strength, soft, and then quenched in temper. Brinell hardness went more than double. Rockwell B, Rockwell C, and the tensile strength. All right, so all quench and temper. They have a meaning. I think the book even explains, so 1,000 or 700, what the difference between them is. So maybe more severe quenching that gets you higher hardness and higher tensile strength. Tensile strength is the ultimate strength, by the way, SU in tables. Yield strength is the other value that you usually find tabulated. And then for elastomers, in terms of toughness, and I mentioned the case was rivets on Titanic, and in general, parts that need to be able to sustain impulsive loading, okay? So there are tests that can be done to make comparisons. There was a time when for the solid mechanics, or rather for the material science class, students were doing impact. There's an impact tester like this one, pendulum tester over in 118. Have you ever been to 118? You can go like right at the end of class. So you lock it in place, and you put a specimen here, either cantilever with a notch or support it between two ends. And the pendulum, you release it, and it accelerates due to potential energy decrease, kinetic energy increase, impacts the specimen, and then it records how far it moved past the lower gravitational potential, and the difference will be the energy lost during impact. So a specimen that takes more energy, that is, the pendulum swings less after impact, would be one that you would qualify as with higher toughness. Okay, so and don't forget, there's the notch that is done to the specimen, which has, it's part of the test. So one is the, let's see, they have different names. So one is the Charpy, and the other one is IZOD test. So with the IZOD test, you have a cantilever. With the Charpy, you have the specimen that's supported. The notch is on the impactor side. Here is the opposite side. And I started saying in material science, they were doing tests with aluminum, but they had them chilled with dry ice. And there's a concept called glass transition temperature, where materials otherwise ductile will behave brittle. You can read, even, I'm sure they have YouTubes where they use liquid nitrogen, and you take a rubber ball and it bounces, and you put it in liquid nitrogen and it shatters. Or a lead bell, you put it in liquid helium and it can ring. A lead bell can ring if cooled. So it behaves, it hardens, behaves different. I was telling you about, Titanic, 4 degrees Celsius, ice floating around, very cold water. And that, for that steel that they used back then, it turned brittle. And there, like I said, there are applications where you want toughness. One example being, say, wheel spindles or piston pins. Okay, you want to have wear resistance as the connecting rod moves relative to the pin. You have friction bearings there, or journal bearings, but then you have the impulsive forces as the firing stroke happens in mostly in diesel. But yeah, it's where toughness is a issue, and elsewhere. There's this concept of creep. It happens at room temperature. If you have a shopping bag that's heavy and you put it on a pin, over time you'll find it stretched. Anybody plays a string instrument like guitar? It's also called stress relaxation for other applications. So you tune a guitar and you put a guitar under your bed, and in 6 months it won't be tuned. You need to retune it. It's both the string and the guitar itself that gives way. But creep is considered primarily for elevated temperature. You have gas turbine blades, and as they rotate, you have centrifugal force, and the centrifugal force may cause the blade to stretch, okay, all the way to fracture. Or furnace component, you have, or maybe cooking stoves. I've seen cooking stoves. I was in the military. It was the kitchen, and they had big, cooking pots, and they use gas to heat them. And that slab, that cast iron slab, they were bowing down because of, over time with the weight of the food, it caused the slabs to bow down. So something to consider. For that reason, gas turbine blades are sometimes made in a single crystal, to where they hold very close to their melting temperature. They hold their strength, they hold their geometry, okay? Although bad thing can happen. We're talking about, there was an airplane that, what was it? McDonnell DC-10 with 3 engines on the tail, and one in the middle, and a blade from that engine in the middle broke and sabered the hydraulic lines, and they managed to land it, but some passengers lost their lives. You can read about that. That was considered a miracle. Anyway, so the company gave a reward to anybody who can find the blade, and a farmer find it 3 months later and return it for the bounty, and they saw they analyzed the type of failure, and were defects in, but this also played a role. elevated temperature in the gas turbine, and centrifugal force that essentially stretches the blade. Specific weight or density classification, we discussed about it's SAE that keeps the updates the designation for various materials just because they use a lot of them, maybe more than aerospace industry. And so the 4-digit designation, this is the carbon content, and this is the alloying number. 1 and 0, it's indicative of or 0, second digit, that there's no alloying element. You can see here molybdenum and chromium, the first 2 digits are 4-1. And how would this translate, as a design engineer? Of course, it's cost. And I was telling you, alloying elements, they're added in order to improve their hardenability. It was less severe quenching. Their components, they are flame hardened or induction hardened. They are not through hardened, so not the entire piece like gears. Use an inductor to just reheat and to red hot and then cooling air to harden the teeth. I can bring you to where you can look at the gear that it's visibly induction hardened. Okay, and then we have, the way they're available. Not all materials available in all shapes. So you need to research and make sure that if you want to use an I-beam, it's available in that grade material that you plan on using. Okay. This is the effective temperature, and it's for elevated temperatures, but we can have one that goes below 0. And as expected, they soften, materials soften as the temperature is increasing, so become more ductile. We use this to do hot forming, forging, including. So do they have a Celsius? This is Fahrenheit. This is less than the melting temperature. What is 1200 Fahrenheit in Celsius? This runs like 500 Celsius, I guess, 400 or 500. And then their strength increase. So if you design for elevated temperatures, you need to be well aware of this kind of behavior for materials. This is time temperature diagrams that are used for heat treatment. So this will be quench and tempering. So rapid cooling for above. This is lower and upper Curie temperature. This is room temperature. And of course, this can happen slower or steeper depending on the quenching medium. And this is the tempering. You reheat it, but below the low critical temperature, and you slowly cool it to undo of the brittleness that comes with quenching. Have you been told of this, like martensite formation during quenching that is brittle but hard? And well, it depends on the bayanite is also a compound that happens through fast cooling. And then you have like annealing, okay, very slow cooling to improve machinability, formability, that is ductility. Quenching and tempering happens to improve hardness. And again, it can happen on the surface or through hardening. So case hardening, just on the outside, or surface hardening. Sometimes you have a low carbon steel, maybe you've been told of this, and then you add carbon to just the surface. You pack it, traditionally it was done packing it with coal dust, and you bake it, and carbon diffuses fraction of a millimeter, and that skin can be hardened, and you provide a hard shell, and then the core remains ductile like a traditional or the original low carbon steel. There are tables that list steels for carburization in the back of the book. Okay, irons. So maybe we'll clarify now what's the carbon content for iron. Yeah, it's left of the a certain iron carbon diagram. I'm sure you've seen this iron carbon diagram. iron carbon diagram. I look at images and tools size large. Do you remember seeing this? Okay, so it says steel and then cast iron. And okay, so actually it's more, yeah, if I said yes at 1.2, actually 2% carbon, it's where irons begin. They have their melting temperature lower than steel. So if you have like a high carbon steel, you see the melting temperature. Irons melt at the lower temperature, and they are also more less viscous. So they make for good casting materials. Okay, this is the eutectic point, the lowest melting point. Okay, and then various allotropic presentations for the carbon and iron in alloys. All right, let's go back to this ductile iron. Depending on alloying element and heat history, you can get various white iron. You get it if you rapid cool it. Carbon does not have time to precipitate. It's hard but malleable. You can get iron just on the surface. Iron, it's a good candidate. You can have crankshafts made of being forged of carbon steel, or could be cast. Aluminums, there are various, pure aluminum is used for electrical applications, like cables, because it's lightweight, it's cheaper than copper. You don't have, long transmission wires made of copper will prohibitively expensive. But yeah, it's used to, is the second best, is it the best, very best electricity conductor is silver. But and gold also good. But the next is copper, and not as good as aluminum, but aluminum is cheaper and lighter weight. Anyway, and then we have aluminum alloyed with various like copper and manganese, you can see here. It can be cast. Cast aluminum behaves brittle. Have a brittle fracture, and then if it's worked, depending on alloying elements, then it behaves ductile. Like you saw the specimen in the round specimen and the flat specimen, sometimes called dog bone specimen. And it can also be hardened through aging. That's the aluminum alloyed with copper. You have the, okay, let's move to copper, brasses, and bronzes. Copper, near pure copper for electric applications, or when heat, low alloying versions or of copper for heat exchangers, for pipes, for AC units, for plumbings. And then if you alloy copper with anything but tin, it gets you bronze. It could be, historically it was tin. Tin is expensive. Copper and tin, you get bronze. Copper and aluminum, you get bronze. Copper and phosphorus, you get bronze. And then if you like copper with zinc, you get brasses. Okay. Good workability, good for bronzes. The good resistant friction. Your bearings made of bronze and other add application. Beryllium copper. Non-magnetic. So beryllium copper is used for non-magnetic parts and springs and such. Zinc alloys are used for casting. Magnesium, very lightweight. There was a student working on, he brought a helicopter piece, made a housing made of magnesium. It was pretty lightweight. There are some vehicles that have magnesium wheels. Maybe, an expensive car comes with magnesium wheel. We like to have them, or aluminum alloy, like them lightweight to help with dynamic suspension behavior. Nickel alloys, stainless steels are steels that have chromium and nickel as alloying elements. There's a section that discusses concrete. You may want, if you're civil engineering major, you may want to read it on your own. Concrete does not behave, does not have a proportional or elastic behavior. So we are just fitting a slope, a straight line, secant line, and there will be a that slope is is noted as, what is it, FC without a prime. And of course, depends on the composition. More cement to the aggregate, the cement mix, it gets you stronger grades than, and depending on where it's used, so you improve strength if you add concrete. Water, if you add water, you lower. You need to minimize the amount of water. Sometimes they use air to homogenize and make it fill the mold when it's poured. Plastics, there are thermoplastic and thermosets. Thermoset materials. Thermoplastic, they soften. Thermosets, it's one-time thing. Once they cure, if you heat them, they just start burning at some point. So for thermoplastic, nylon, like this long specimen, this is nylon. Polyethylene, and of course depends on the size of the molecule. Low density, high density polyethylene. High density would be longer molecule, longer chains. ABS, they're transparent polyurethane. Again, I'm assuming that this was taught to you in material science. You'll hear this again a little bit more detail in manufacturing processes. Composites, we discussed composites. So many applications nowadays where use of composite was the key to their development. Wind turbine blades, before composites, you think only like what? Maybe wood, shingles. That is the windmills in some places. They use sails. But yeah, composites, they reinforce. You have reinforcements, and the way you form the composite, you would need a mold, and the way you cure it in air or autoclave. Maybe somebody that works on boats made of composites. Sometimes there are businesses in town, or what? I'm sure you've seen. You can drive not too far to find the business that installs swimming pools made of composites. And you look on the outside, or bathtubs. If you go to a construction site, you can tell the random fibers to the inside, the finished inside surface. They're formed over mold. They use what are called pre-pregs. That is, they present themselves like these. They're pre-impregnated fibers. Could be glass fiber. And the size of the fiber, orientation matter. It could be mesh. And then you have what? Carbon fiber. Carbon fiber are just nylon fibers that are baked until they turn into carbonite. And they're rather short. You don't see it. They're brittle in case you have handled, composite was maybe fractured. You can see the presentation of the flakes. Again, a rich subject here. You can take a course, maybe in Keensville. I know there's a gentleman named Peel that does research on composites in Keensville. Have you heard of him? Sometimes I know of a student in the past that did the master's in Keensville. We'll start a master program in fall. The hope is, not the hope, the plan. With various benefits, the remainder of the chapter talks about how you can estimate the properties of a composite. Of course, matters what the matrix you use. That is, what kind of resin. That can be thermoplastic or thermosets composites, depending on application. So thermosets will be like epoxy. Thermoplastic, they use polyethylene, for example. Really, if you look at, there was a lab that we did for manufacturing process where I had students dissect a small power tool, like a jigsaw or reciprocating saw bought from Walmart for less than $30 per piece. And I asked them to, extract as much information. One was to identify how the housing was made, and you can even tell the filler. So that doesn't qualify as a composite material, but in order to save cost, plastic used to make housings for, like I said, that kind of power tools, they have filler materials, and it could be in the form of fibers. You can see the short filaments of on the inside, the not essential to be aesthetic surface. Again, a rich subject. I'm not quite the material science person. As a design engineer, you learn of the specifics of the company you're working with. In Texas, you can find places that they use composites, fabricate helicopter components for Bell helicopters. We had students who graduated from here and worked for Lockheed and for Bell. I was telling you a student for that find a job was Boeing, working with strain gauges. Okay, so the last portion of this chapter discusses about material selection. And there's some pretty popular, a book I know by name one of Chabon, one of the co-author, and tells you how you can, based on density and strength, what kind of material could be good candidates, So and all here listed. So silicon carbide, aluminum alloy, silicon nitride, silicon oxide. That's a aluminum 2, oxygen 3. It's one of the very hard material that you can get. Ceramics. Essentially, these are ceramics. Okay, so yeah, this was it. There's some conceptual problems. Name 5 varieties of cast iron, 4 type of steels. So what would be the 4 type of steels? Low, medium, and high carbon steels, and probably stainless steel will be the 4th one. What's the ultimate strength, yield strength, and percent elongation of SE 1040? Okay, so what do we do about this? You have a problem, not here, later in the chapter or in the book, and it says SE 1040. And it's hot rolled. And you want to ultimate strength, yield strength, and percent elongation. Go to the back of the book, and if the percent elongation is more than 5%, and you'd expect it, then you use the one approach in terms of design factor selection for brittle material, which is not the case of this one. Others are the recommended design factors in design problems. Direct stress, deformation, and design. Okay, so we're moving to chapter 3, and this is where essentially we learn about design factor and why it's chosen as such, and then is where we can move just one step further to all that we've done so far. You calculate an actual stress, which is a design stress, and how do you relate it to the properties of material to report the design factor, or maybe calculate the required cross section, or choose the type of structural steel, say, or section for an application. Okay, so we've seen this before. To calculate direct stress could be I by tensile compressive. You divide the axial load by the cross-sectional area. You saw that in the tensile testing, the stress is calculated with the area as is, no correction for its change, although it can happen for large deformations. But the assumption is that there's no additional effect. You don't induce bending by having, and it can be rather easily. So if I have this, assuming this being a specimen, so it's one thing to apply straight in the middle the load, but if you put it on a side, you will induce bending to it starts, if you tip it, it's indicative that this area here is no longer going to experience stress. It's shifted. The stress distribution in the cross-section is other than a uniform one, which no longer makes this equation valid. You actually have bending on top of axial loading. It's what we say. So the choice of design factor, sometimes called factor of safety. It depends on the behavior of the material, whether it's ductile and whether it's brittle. It also depends on the type of loading. So brittle materials don't do well when you have pulsive, that is impact loading. And with the things that we learn in this class, the correction is made in the choice of ultimate strength as a reference property of the material and the type of design factor. We looked at appendix, what was it, 17 was a summary of design factors. Back then I just say design factor or factors of safety. We don't use factor of safety as much because design factor is a more broad concept. Okay, not everything causes an unsafe circumstance if it fails. It could be just a nuisance. Okay, but there's code, there are standards, and I listed. So it says brittle material, material strength basis, in manner of loading, static, repeated, or impact or shock. And when you choose a design factor, again, you're responsible. You need to know what can happen during the life of the product and what the effect of failure could be. So a design factor captured uncertainty about the load, the possibility of overloading. Then let me project the actual section. So yeah, it says manner of loading, but design factor captures overloading due to misuse. So you cannot anticipate that happening. It's too complicated. You simplify the part. So what do you say? The engineers approximate a horse with a spheres to make the math easy. You approximate a rather long part with a continuous beam, but it might not be. Or a beam in bending has to be rather long, but we approximate and use the beam theory for short beams like teeth in a gear in a first approximation. And then what happens, you can have after or during its use, you have environmental effects. And corrosion can weaken, it can be places where a fracture can develop and grow into a full fracture. And size. The small size does better when it comes to fatigue, but also strength. So thin wires are stronger than thicker wire because of the strain hardening effect. A pair of small size sports shoes lasts longer than a pair of bigger size sports shoes. Do you agree with this? You live in the area where Nike headquarters is it right? Yeah, aren't they based in Portland? Okay, so well, you may say because the size of Nike sports shoes or sports shoes are worn by a bigger person on one hand, but in general, if you think that they're small, they're compact, the thickness of the leather is less, and the span. Anyway, on going a little bit on a tangent. So size effect, mass effect. And then it says here, quality control. I said aerospace industry it's much stricter upon the properties of the materials they use. They require bulletins, test bulletins with every batch they receive is not within their accepted limits. They reject it. They're not as generous. Give or take 15% might not work for them. Give or take 3% might be what they accept over catalog listing, and then hazard presented by failure. So it's one thing, like a wheel stud to fail, you lose a wheel, there's an accident, versus not that either is desirable. So you lose the bolt that connects the drive shaft to the rear axle in a truck. If it fails, you drive out of traffic and call for help. And then cost. the best for the job might be prohibitively expensive. As a design engineer, there's their slogan: use the worst good material. Worst being, you think worst being cheaper, right? If you order a steel with alloying elements that are expensive, and I listed nickel as expensive one, tin is also expensive. You can look up online, like how much does it cost a pound of copper is also expensive. There's a raw copper. For the project that I had to order, it wasn't long, like 3 inches by 1 inch copper bar, and I paid $50 for it. So yeah, cost. So just for cost reasons, you may settle to not the best, and you need to maybe oversize to compensate, or not oversize, reconsider the size, go with heavier loads. Yes. Good point. So ask the U.S. Mint, but definitely does. That's why they are made of. They made them of copper, and then I think you can look up the history of the penny. During the war, they shipped copper as a strategic material used for brasses for cartridges and other uses. Yeah, probably it's not worth having pennies in circulation anymore. They're irrespective. They're more expensive than the face value. The $100 bill is a good business to be in. Good luck, U.S. government. So it costs 20 cents to print a $100 bill. Did you know that? With all the inflation, I think it used to be 18 pennies to print a $100 bill last year. So you go with one of those and you buy a barrel and a half of oil. That's why some countries don't like it. Time is up. 1:54. Looks like they have a class after us, so we cannot extend the conversation for too long. But I would recommend you, this is good information to be aware of. Heard of it once, and I'm talking about chapter 2, because you go to a job interview, and if you have, if you can speak their jargon, and it's not jargon, it's just the engineer's knowledge that you can engage in a conversation, you will be looked at with more consideration, and you may get that job, if it makes sense. I remember a student, it was a few years ago, they asked for the second round of the interviews to come in with a solution to a problem that they gave. And it was pretty much like what I discussed. He visited with me. He was smart in general and smart enough to check with me. So it was a company that says, design us a shaft for a pulley system that is holding the cable to support the submersible to service underwater wells. Okay? And we talked for a little bit, and I said, well, you know what? If you're into fishing, you know very well that that the line, currents pull on it much more than the weight at the end. One thing to consider. And then we looked at how to support it on bearing. Short shaft is better, and he got a job. So it's not unheard of. They ask you. More recently, a student for a job interview presented a project he did for design of machine elements. For the other class, mechanical systems design. So some employers may say, I wish this is a good choice. Let's hire him and C or her. And others may be more savvy and say, show us what you know. It doesn't hurt to be able to go there and say, oh, by the way, this is my problem book for the strength class. What do you think? Oh yeah, I remember. Yeah, there's a beam. There's a they went into management 10 years ago. Barely remember. Well, let's not speculate, but don't hesitate. What? Last that goes on camera. Jules Renard is saying, my father, good guy, told me once, don't use your ignorance. You will never be able to replace it. Okay? Don't hesitate to learn stuff that it may help you. You never know. Maybe for the second job, third job that you will be taking. Not the first one. Anyway, so we'll stop here. We'll see you tomorrow for the FE quiz. And